Hello everyone, I am Muhammad Ahsan and my partner is Samiullah. We are from National Junction University and today we are presenting on atomic bonding in materials. We will explain how microscopic bonds determine whether a material acts as an insulator, is semiconductor or a conductor. So basically bonding explains why solid exist, why atoms do not simply fly apart and why materials show such a wide variety of physical properties. In condensed matter physics, bonding forms the bridge between atomic scale quantum mechanics and microscopic material behavior. Throughout this talk, we will gradually move from basic bonding concepts to more advanced ideas such as band structure, phonons, and electronic properties relevant to modern research. Bonding is important because it determines almost every physical property of a material. Electrical conductivity depends on whether electrons are tightly bound or free to move. Thermal conductivity depends on how atoms vibrate around equilibrium positions, which is controlled by bond strength. Mechanical properties such as hardness, elasticity, and brittleness arise from how strongly atoms are held together. From a condensed matter perspective, bonding determines band gaps, density of states, and carrier mobility. When we engineer materials for electronic, photonics, or quantum devices, we are essentially engineering bonding at atomic scale. This slide shows the logical chain of solid state physics. Everything starts with atomic bonding. Bonding defines how atoms arrange themselves, forming a specific crystal structure. The crystal structure determines how atomic orbitals overlap, producing the electronic band structure. This band structure controls whether electrons can move freely or are confined, determining if the material is metallic, semiconducting, or insulating. Bonding also determines phonon modes which control thermal conductivity and electron-phonon interactions. Ultimately, all measurable material properties originate from this chain. Atoms bond because bonding leads to lower total energy and greater stability. This principle applies universally in physics. When atoms come close together, attractive forces lower energy while repulsive forces increase it. A stable bond forms at the distance where total energy is minimized. Quantum mechanics is essential here because electrons are not classical particles. They are described by wave functions and bonding corresponds to a redistribution of electron probability density that minimizes energy. This is why classical physics alone cannot explain bonding in solids. Ionic bonding occurs when one atom donates electrons and another atom accepts electrons. This typically happens between metals and nonmetals with large electronegativity differences. The donor atoms becomes a positive ion and the acceptor becomes a negative ion. The bond itself is the electrostatic attraction between these oppositely charged ions. Because electrons are localized around ions, ionic solids generally do not conduct electricity in the solid state, making them good electrical insulators. These examples illustrate how common ionic bonding is in nature and technology. Alkali halides such as NaCl are textbook ionic crystals. Oxides like MgO and Al2O3 are extremely important in ceramics and electronics due to their high melting points and chemical stability. Whereas sulfides and carbonates are widely found in minerals, while the nitrates and sulfates are crucial in chemical and industrial processes. All their properties are directly linked to strong ionic bonding. In solid state, ions are fixed in lattice positions, so electrical conduction is not possible. When ionic solids are molten or dissolved, ion becomes mobile, allowing electrical current to flow. But mechanically, ionic solids are hard but brittle. When stress causes layers of ions to shift, like charges may align and repel strongly, which will lead ultimately to the fracture. These high melting points arise from strong Coulomb forces that require large energy to overcome. Now, if we talk about classically, then classically ionic bonding can be described using Coulomb's law, which explains attraction between charges. However, this approach cannot explain why electron transfer happens. So then we have to move towards the quantum mechanics. So quantum mechanically electron energize and the orbital overlap and the total energy minimization explain this electron transfer. The Born-Oppenheimer approximation simplifies calculations by separating fast electronic motion from slow nuclear motion, and this is a cornerstone for solid state theory. Ionic solids from regular crystalline lattices that maximize attraction and minimize repulsion. High coordinations numbers are common in this situation. So if we see optically, then the wide band gaps mean these materials often transmit visible lights, which makes them transparent, whereas chemically they dissolve in polar solvents when hydration energy overcomes lattice energy. This is a very important concept in electrochemistry and materials science. Now, if we talk about the covalent bonding, then the covalent bonding occurs when atoms share electrons rather than transfer them, which fundamentally distinguish it from ionic bonding. This sharing happens when atoms have comparable electronegativities. So neither atom can completely dominate the electrons. In covalent bonds, electrons occupy regions between nuclei leading to strong directional bonds. This directionality is extremely important because it determines bond angles, coordination number, and crystal geometry. If we look from a condensed matter perspective, covalent bonding directly controls orbital hybridization. This hybridization determines how atomic orbitals overlap in space, which later evolves into energy bands.
My name is Samiullah and I am going to carry forward what my partner says. In non-polar covalent bonds, electrons are shared equally because both of the atoms have nearly the same electronegativity. As a result, the electron clouds remain symmetric around the bond axis and no permanent dipole moment is formed. This symmetric charge distribution has important physical consequences. It means that no internal electric field associated with the bond, which affects the dielectric response and the optical activity. In solid-state physics, nonpolar covalent bonds leads to the well-defined block states without strong internal polarization fields. This is why materials like silicon show relatively clean electronic band structure, making them ideal for controlled doping and device fabrication. Nonpolar covalent solids are typically network solids, meaning atoms are bounded extended in three-dimensional frameworks. Rather than discrete molecules, each atom strongly bound to the several neighbors through directional covalent bonds. Because these bonds are strong and localized, such solids are often exhibits high melting points, mechanical rigidity, and low compressibility. From a phonon perspective, strong covalent bond resulting in high phonon frequencies which directly influence thermal conductivity. This is why material like diamond have exceptional high thermal conductivity despite being electrically insulator. Now, this slide explains the diamond represent the extreme case of covalent bonding. Each carbon atom forms four sp3 hybridization bond, create a rigid three-dimensional lattice. This explains diamond's extreme hardness, wide band gap, and high thermal conductivity. On the other hand, silicons also form sp3 hybridization's covalent bond, but the larger atomic size reduces the orbital overlap, resulting in small band gaps, which makes silicon semiconductor not an insulator like diamond. Control breaking covalent symmetry through doping allows the charge carriers to move. Graphite also demonstrates how bonding anisotropy changes the property. The strong sp2 covalent bond exists within the planes, while weak interlayer interaction allows this to slides. This leads to high in-plane electrical conductivity and mechanical softness in one direction in graphite materials. Now, moving to polar covalent bonds. Polar covalent bonds arise when electronegativity differences are moderate, large enough to distort the electron cloud but not large enough to control electron or transfer electron. This result partial charges and permanent dipole moments. The internal dipole interacts with the external fields, strongly influencing the dielectric constant polarization and optical response of the material. In condensed matter physics, covalent bonds are essential for understanding the ferroelectricity, piezoelectricity, and polar phonons, which play a major role in infrared electronic optics and electron phonon coupling. Now, in polar covalent bonds, in R is the oxygen hydrogen the bond between the oxygen and the hydrogen atoms combined with the hydrogen bonding create upon lattice structure. This explains why ice is less dense than water, which is a very rare and anomalous behavior in the which has a huge environmental significances. In quartz of the silicon dioxide, bonds break the inversion symmetry, enabling its piezoelectrical behavior. Mechanical stress induces the polarization, and applied electric field induces strain. In polymers, polar covalent bonds introduce dipole-dipole interactions, which control glass transition temperature, flexibility, and mechanical strength. This is crucial for polymer engineering. Okay, now continuing to the comparison of the polar and non-polar bonds. This table summarizes fundamental physical consequences of the bond polarity. Non-polar system relies mainly on weak dispersion forces, which leads to the lower boiling points and weak intermolecular cohesion. In polar system, which exhibits the strong dipole-dipole interaction and hydrogen bonding, resulting or leading to the higher boiling points and greater solubility in polar solvents. From a material point of view, polarity controls the dielectric response, solubility, mechanical softness, and thermal stability of the material, making this distinction crucial in material selection in condensed matter physics. Now, the classical description of the covalent bond. Classically, covalent bonds are described using Lewis structure where electron pairs are drawn as shared lines. While this representation is useful only for chemical intuition, it treats electrons as localized particles which actually are not. This approach fails to explain electrical conductivity, band gaps, or optical absorption in solid. It also cannot describe how millions of atoms interact coherently in crystal. Thus, classical descriptions of the covalent bonds are limited to small molecules and must be replaced by the quantum mechanical explanation in quantum mechanical models and condensed matter physics. So, moving to the quantum mechanical explanation or description of the covalent bonds. Quantum mechanically, covalent bonding is explained through orbital overlaps. When atomic orbitals overlap constructively like waves, bonding states with lower energies are formed. And when the atomic orbitals overlap destructively, the anti-bonding state and high energy states are formed. Pauli exclusion principles explain and restrict that each orbital will have two electrons with opposite spins. In solids, bonding and anti-bonding orbitals are broadened into the continuous energy bands due to the interaction among many atoms. The energy separation between these bands defines the band gap, which determines whether a material is an insulator or semiconductor or metal conductor. Now, moving to the other type of bonding, metallic bonding. Metallic bonding occurs when valence electrons are not localized with specific atoms but are instead delocalized over the entire crystal. It seems like the positive ions are immersed in a sea of the electrons, mobile electrons. This delocalization explains why metallic bonds are non-directional and why metal can deform plastically without any breaking. From quantum perspective, metallic bonding arises when atomic orbital overlaps so strongly that electrons are no longer associated with individual atoms but flow like sea between the lattice atoms. In the perspective of the band theory, as atomic orbitals overlaps in metals, discrete energy levels merge into continuous bands. Unlike semiconductors, the valence and the conduction bands overlap here, or the Fermi level lies within the partially band, filled band. This allows electrons to respond immediately to the external fields, electric fields. The absence of the band gap is fundamental reasons metal conduct electricity easily. Band theory also explains why small changes in structure or composition can significantly alter the metallic properties.
Now, this slide summarizes why metals behave the way they do, and all of these properties originate from metallic bonding and delocalized electrons. First, electrical conductivity. So, the metals conduct electricity because a large number of electrons are free to move. When an electric field is applied, these electrons drift and create current. However, electrons do not move freely forever. They scatter from lattice vibrations called phonons and form defects. As temperature increases, phonon vibrations increase, leading to increased scattering and reduced conductivity. The thermal conductivity in metals is also dominated by electrons rather than phonons. Electrons transport kinetic energy from hot regions to cold regions. This is why good electrical conductors are usually good thermal conductors as well. This relationship is captured by Wiedemann-Franz law, which connects electrical conductivity, thermal conductivity, and temperature. Mechanically, metals are malleable and ductile because metallic bonds are non-directional. When stress is applied, atomic layers slide, but the electron C redistributes and maintains bonding. Unlike ionic solids, bonds do not break catastrophically. Optically, free electrons interact strongly with electromagnetic waves. Incoming light induces collective oscillations of electrons, leading to reflection. This is why metals are shiny and why their color depends on electronic transitions. Metallic properties are strongly influenced by crystal structure, not just chemical compositions. So, metals typically form close packed structures to maximize atomic coordination and minimize energy. In FCC and HCP structures, atoms are packed very efficiently, giving high density and good mechanical stability. This is why FCC metals like copper and aluminium are highly ductile and easy to shape. BCC metals have lower packing efficiency but often exhibit higher melting points and greater strength at elevated temperatures. Tungsten is a classic example which makes it useful in high temperature environments. Melting point variations among metals arise from differences in electron density, bonding strength, and crystal structure. Heat capacity is also influenced by lattice vibrations and electron contributions, both of which depend on bonding strength. This table highlights how bond strength directly correlates with melting point. Mercury has extremely weak metallic bonding, which is why it is liquid at room temperature, whereas sodium also has weak bonding because it contributes only one valence electron per atom. As we move to metals like aluminium and iron, the number of valence electrons increases, strengthening metallic bonding. Iron's strong bonding explains its high melting point and mechanical strength, whereas tungsten represents an extreme case with high valence electron density and strong orbital overlap lead to exceptionally strong metallic bonding. That's why tungsten has the highest melting point of all the metals. And from a condensed matter perspective, this trend reflects increasing bandwidths, electron density, and cohesive energy. Now, this slide moves into more advanced condensed matter concepts. The Fermi surface represents the boundary between occupied and unoccupied electron states at absolute zero. Its shape determines electrical conductivity, magnetoresistance, and many transport properties. Small changes in bonding or structure can significantly distort the Fermi surface, leading to dramatic property change. Plasmons are collective oscillations of conduction electrons instead of individual electrons moving independently. The entire electron gas oscillates coherently. Plasmons are central to plasmonics, nano-optics, and photonic devices where light-matter interaction is engineered at sub-wavelength scales. And the superconductivity arises when electrons form bound Cooper pairs through phonon-mediated interactions. Even though electrons repel each other, lattice vibrations enable effective attraction. This phenomena cannot be understood without a deep understanding of bonding and electron-phonon coupling.
Now, moving to the work function in thermionic emission. The work function is the minimum energy required to remove an electron from a metal surface into vacuum. It depends upon the bulk bonding, surface orientation, and electron density, which is applicable in the photovoltaic cells. Strong metallic bonding generates leads to the higher work function because electrons are more tightly bound. Thermionic emission, on the other hand, occurs when thermal energy allows electrons to overcome the work function barrier. As temperature increases, more electron gain sufficient energy to escape. This principle is fundamental in vacuum electronics, electron microscopes, cathode ray tubes, thermionic energy converters. In condensed matter physics, work function engineering is critical for contacts in electronics and optoelectronic devices. Quantum mechanical description of metallic bonding in metals. Classical models fail to explain many metallic properties, so quantum mechanical explanation is essential. The Drude Sommerfeld model treats conduction conduction of electrons as a quantum gas confined within the metal. These electrons obey Fermi-Dirac statistic, not the classical statistics like Maxwell-Boltzmann statistics. Only electrons near to the Fermi energy can respond to the external fields. This explains why electronic heat capacity of metals is much smaller than the classical predictions. The Pauli exclusion principles restrict the electron occupancy, shaping the density of the states and the transport behaviors of these materials. This quantum model formed the basis for the modern electronic transport theory. Now, moving to the other forms of bonding, which are not main types of bonding but crucially control the properties of the material. The London dispersion forces. London dispersion forces arise from instantaneous fluctuation in electron density. Even in non-polar atoms, electrons are constantly moving, creating temporary dipoles. These temporary dipoles induce dipoles in the neighbor atoms, leading to the weak interaction between the atoms. Although these forces are weak compared to the ionic or covalent bonding, they become significant in large systems with many atoms. In condensed matter physics, dispersion forces play an important role in layered material, van der Waals solids, and molecular crystals. They are essential for understanding material like graphite, metallic oxides, and other 2D materials. Vector affecting the London dispersion forces. The strength of the London dispersion forces increase with the polarizability, which depends on the size of the electron clouds. Larger atoms with more electrons are more easily distorted, leading to a strong dispersion forces. Molecular shapes also matters. Extended flat molecules experience strong dispersion forces due to increased surface contact. This explains why boiling point increase down noble gas group, why large organic molecules can form stable solids even without strong chemical bonds. Now, another type of bonding is dipole-dipole interaction. Dipole-dipole interaction occurs between molecules with permanent dipole moments. These interactions are directional and stronger than the dispersion forces but weaker than the covalent bonds. Hydrogen bonding, it is special, unusually strong dipole-dipole interaction that occurs when hydrogen is bonded highly to the highly electronegative atoms like nitrogen, oxygen, or chlorine. Hydrogen bonds responsible for water's high boiling point and its hexagonal structure of the ice. The structure of the ice and the stability of the biological molecules like DNA and proteins. In condensed matter physics, hydrogen bonding play a crucial role in soft matter, polymers, biological material, and proton conducting systems. Now, the implications of the bonding in the condensed matter physics. This final slides connects everything together. Bonding determines how atomic orbitals overlaps, which leads to the band structure formation, the presence or absence of band gap that defines whether a material will be metal, semiconductor, insulator, or topological insulator. Bond strength and atomic mass determines the Ponan spectra, which controls the thermal conductivity and the proton-electron interactions. Crystal structure reflects optimal bonding geometry, balancing the attractive and repulsive forces. Ultimately, understanding bonding allows us to design a material with the desired electrical, optical, mechanical, magnetic, and quantum properties. These foundations of the condensed matter physics and the modern material science. Thank you.